Thank you very much, Martin, for talking to me today about your book, Once Upon an Algorithm: How Stories Explain Computing. I'm wondering maybe if you could say a little bit about the impetus for this book and why you decided to take this idea and put it together in such detail as you have here, using obviously computer algorithms and computer science, but also in a language that is very accessible to people who are familiar with stories like Hansel and Gretel and similar things like that. Why did you decide that this was a project that you wanted to take on?
Yeah, so I'm a big fan of popular science books, and there are many books out there that explain, for example, evolution or quantum physics, psychology, economics, and so on and so forth. But there are not so many books on computer science available, and I thought, well, that should change because computing is growing every day in its impact on our lives. And so people should have a chance to understand what computer science is about, what computing is about, what an algorithm is. And that was the original motivation. So I wanted to write a popular science book about computer science. The question how the stories came in, that's probably related to the fact that when I go to work every day, I take the bus, and my bus ride is about 7 minutes long. And so with my bus buddies, we often talk about all kinds of stuff. But whenever they ask me about my work or what classes I am teaching, I always try to start from the bottom up. Like I explain computing or computer science in the classroom, and the time is never enough. And it was really hard to get across what I and my students are working about on, and what the particular topics are about. And so I had to find some metaphors to get this across more easily. And at some point in time, I had the idea of just using stories or elements of stories to doing that. And yeah, these two things came together, and well, that was when the idea for this book was created. And then I looked for more stories to cover a broad range of computer science. Yeah, that's how this came about.
What did you start with, if I can get a sense of how you worked on the book? Did you think about stories and then how an algorithm would fit that? Or did you think about an algorithm that you wanted to talk about and then how maybe a story would work? How did you put these things together?
The original goal was to explain several aspects of computer science. I was first asking myself, well, what does a layperson have to know about computer science in order, well, to get a good impression of the field? Algorithms are certainly a central topic in computing, but it's not all. There's also the second part of the book is concerned with languages and language concepts. Mm-hmm. And so I first created basically a map or table of contents of concepts, basically, that everybody had to, or that I thought everybody should at least know a little bit about. And then I started to looking for stories that would be fitting and that could be used to explain those ideas. The first one was actually Hansel and Gretel. That example was really a very good one for explaining algorithms and many subtle aspects of algorithms that even somebody who has a very rough idea of what an algorithm is probably doesn't think about. The notion of runtime, the notion of termination, the question of representation, the question of how it is actually possible to solve problems using algorithms. So all these things could very well be explained with Hansel and Gretel. But then, yeah, finding examples for other concepts, that really took some time to find stories that were fitting and broad enough in scope to explain the concepts, but also well enough known so that, people could connect to it.
And it seems like you had a number of other possibilities. I mean, in the chapters, you often mention other stories that fit similar patterns. What made these ones stick out? I mean, so generally speaking, for anyone who hasn't read the book, right, you start with Hansel and Gretel, you have Sherlock Holmes, Indiana Jones, Groundhog Day, Back to the Future, Harry Potter, but you also mention dozens of other books. How did you pick these ones?
So when you go look into the details, then sometimes a certain aspect fits very well with one story or one movie or whatever it is, but then another aspect really is lacking. And so I had to really comb through all these different possibilities and find those stories that, well, offered the most. And I also, the book tries to use one story at least for 2 chapters, for at least covering 2 different aspects. Indiana Jones is used for 3 chapters. Mm-hmm. So to get this breadth, I didn't want to have one story for each individual aspect. Then it would have been too much. And I want to use one story as much as possible for illustrating certain ideas. And so that led to this filtering process. And in some cases, I went back and forth between 2 or 3 different stories and finally settled on one. And there's no algorithm to do this. This was really a judgment call. And it took some time to actually arrive at this.
Was there anything that you found surprising as you were trying to decide how to come up with the best metaphor or allegory for the computer technologies that you're talking about? I'm curious if you thought a story would work and then you realized it didn't, or if you thought a technique for comparing would work and then there were some glitches. What, if anything, surprised you about that process?
Yeah, one example is maybe the first 2 chapters about language. And I first thought, language, that is easy. I'll take Alice in Wonderland or Through the Looking Glass, which are well-known stories, and language plays a prominent role in those stories. And I thought, well, yeah, I can use those stories very well. But then I noticed that, first of all, the way language is used is in a very specific way. It's on the word-by-word level and not so much on a sentence level. And so that was one thing that was what made me stumble. And the other thing is that if you use English to explain language, then you're too close to the subject matter. So I needed a domain that is slightly removed, where you're not confused whether you're talking about language itself or confuse the example with the concept being explained. And using English to do that, well, this was just too hard. I mean, you can see this in one of the earlier chapters when I talk about representations, the fact that certain names stand for something else, and I have to use quotation marks. And this is already very technical. And this would have been a nightmare to do in the chapter on languages. And so that's when I finally decided not to use Alice in Wonderland and actually use a music piece to explain language. And that allowed me to keep the distance between the domain I use for explaining the concept and the concept itself. Because it's not so obvious at first that a music piece is a sentence in a language, but it is. And once you see the relationships, well, then I think this works very well as an explanation. So that was a surprise maybe. And yeah, it took some time to realize that the low-hanging fruit in this case was not really the sweetest fruit.
No, that was interesting. I thought that it worked really well with the notes and the way that you talk about music as a language. Mm-hmm. I think that one of the things that interested me, because the podcast itself that I've been doing for almost a year now is really about cultural studies and philosophy, which is not really where I would say your book fits. Mm-hmm. Not explicitly, mm-hmm. but it does relate to a lot of the ideas that people are talking about in cultural studies and philosophy, which is really the question of how computers and humanity and society fit together, and in what ways they do and in what ways they don't. So just to start with that conversation, why do you think it's important that people understand how computers work? Especially, as you said, this is a sort of popular science book. And so it's not directed at the computer engineers necessarily, but at a broader audience. Why is it important for a broader audience to understand these concepts?
Yeah, so, well, it's first of all, it's obvious that computing affects more and more areas of our lives. And most of us actually use computers in some form or another. I mean, cell phones are computers, and many people use laptops or desktop computers at work or at school or at home. From that perspective alone, it's interesting and instructive to have a little bit of knowledge about what you're working with. But then even if you don't use computers actively, you're still affected by computation. So traffic control, when you're at a doctor's office, all these devices are, or many of these devices are computer controlled. And or think about self-driving cars. Now we have reports of these accidents that happen now. All of a sudden, we have to think about what it means to give control, very important control of our lives to computers. But then even if you go further, even if you take away all electronic machinery, then still computing is a huge part of our lives. If you consider many things that you do on an everyday basis, they are very algorithmic. If you get up in the morning and dress, you're kind of executing an algorithm. Or if you make breakfast, or if you commute to work, algorithms are with you every step of the way. And so it's just a good idea to understand what you're doing and what your life consists of. And then on a broader level, it's not really surprising that computing gets more and more importance and is taking over more and more of our lives, because ultimately an algorithm is just a systematic way of solving a particular problem, a problem that can reappear, like making breakfast. And so if you think about this, we as humans or as any species is constantly confronted with problems, and we have to do problem solving. And so having invented or discovered a way of systematic problem solving, well, it's no wonder that we use this more and more and more. And now, since we can automate it, that this will be done more and more by machines. And so that's why computing is really a part of everybody's lives without even knowing it. And so it's probably a good idea to know a little bit about it. That is kind of the deeper reason, I think.
Well, and of course, that makes a lot of sense. One phrase that's always captured my attention was, I think, Douglas Rushkoff. I don't know if you've heard of this book, but he has one called Program or Be Programmed, which is really an interesting concept to me of maybe embodying some of the ideas that people are both worried about but also excited about, because effectively you have these two groups, right? You have programmers and people who understand programming, and then you have those who are at its mercy almost. Would you say that you sort of share this idea of a two-sided society where one side is able to understand and program and others aren't, or do you see it in a different way? How do you see the relation of computer programmers to the rest of society?
Well, when we're talking about programming, this can mean different things. Of course, when you think about programming a computer, knowing a programming language, those programmers in this sense, they are of course different from the vast majority of people who probably do not know how to program a computer. Although people may actually underestimate their ability and actually their activity in terms of programming. So whenever I talk to people about this, I ask them whether they have ever used an Excel spreadsheet, and most people have. And whenever you're putting a formula into an Excel spreadsheet, then you are actually programming, and you are a programmer. It's a very simple programming language, but nevertheless, you are creating a program. You're creating an artifact that, if you put in different numbers in the cells that are referenced by the formula, then this program is re-executed and computes new values. So I think people are more programmers or are programmers to a larger degree than they realize, even in this narrow sense of programming a computer. But then, of course, you are right. Professionals, they have a lot of impact in what they do. But I think this is true with any scientific or engineering discipline. People who build cars or build airplanes, they have also a lot of impact on all of society and people who use these devices. So I don't, maybe computing is right now a very important and very powerful force in this respect, but I don't think it's principally different from other areas of science that are then used by engineers to create technology that impacts society. And actually the purpose of writing popular science books is to not embrace, but actually overcome this dichotomy that we divide society into those that are programmers and those that are programmed. This, I think nobody should consider themselves as being manipulated in this way. And being informed is the first step as resisting such a scenario.
Well, what you're doing, I guess, is in a very simplified version, using literature, popular culture to an extent, to explain computer programming. It made me think of a different book called Distant Reading by Franco Moretti, who kind of does the opposite and tries to explain literature by using computer programs. So he'll put in a bunch of books, right, and find out kind of the scenarios that keep coming up, or the patterns that arise that a normal reader would never be able to figure out because of the computational power involved. But a lot of people sort of worry or resist or again, coming back to this dichotomy that computers shouldn't be infringing on literature or the humanities or the arts because those are separate spheres. I'm wondering how you feel about that and whether there is a sort of line where this stops becoming a realm of computer science or even generally speaking, just algorithms, and it becomes something else, something art. Or do you think that the two shouldn't be divided in any way? How do you feel about that relationship that some people have embraced and some people have tried to put up markers?
Yeah, so I actually talk a little bit about this in a similar way in the last chapter of the book, which is about abstraction. And I use actually stories as an example for which you can use abstraction. So you can see certain patterns reoccurring in stories, and you can capture these patterns using abstractions, using functions or procedures. And then by filling in values for parameters, you can instantiate these patterns, these commonalities that you have identified to the different examples. So that is not necessarily, well, that is neither a good or a bad thing. That is just an observation. You can just observe that certain characters or certain storylines appear over and over and over again. There's this book, or there's actually several books on these 7 basic storylines that have been identified since antiquity. And well, that's really just a reflection of this fact that we can and we do see patterns in everything. And we use we use the notion of abstraction to just organize and understand the world. And so we do compare different instances of in arts, in literature, and we cannot help doing it. And so this doesn't mean, that we now have to write programs that create stories, although some people have done that. And sometimes maybe this works, sometimes it doesn't. And this doesn't take away from or doesn't diminish human creativity. It's just, I would say it's just, first of all, an observation that you can apply abstraction, which is actually maybe the central concept of computing. So most people would know the word algorithm, and they know computing or computation. But if you had to ask me what the central notion of computing is, or computer science is, it's actually abstraction. It is widely applicable, and I explain this in the book in the last chapter. You can certainly apply it to literature and other forms of art. I don't think artists or writers, poets should be threatened by this in any way, and in the same way that a painter shouldn't be threatened by the fact that you can analyze the paint and determine what kind of molecules it's made of, and or that if a painter or an artist draws a certain or creates a certain drawing and you can identify certain relationships mathematically, well, that is not a threat to the art. I think it's just a different way of looking at it and understanding it.
Do you think that, I mean, maybe part of the issue in people who resist the, I guess, idea of computers and computing encroaching on new territories is that it could at some point become more creative? I mean, in terms of artificial intelligence and in terms of its ability to go beyond what we have now. Do you see computing as a creative endeavor, and if so, how?
Yeah, so this whole discussion on AI and how powerful AI, and then also how threatening AI can be. So there's several things you can say about this. On the one hand, AI is very powerful in specific areas and very useful too. It can also have harmful effects, no question about it. And that is true of computing and computer science as it is for any technology. As far as human creativity being threatened by artificial intelligence creativity, I don't know how threatened we should be feeling about this. There are algorithms that you can feed music into, and they create music that sounds similar. But in many of these instances, yeah, they can replicate certain musical styles, and the same is true for visual arts, I think. But well, and maybe by combining certain elements, they can also create something new. But I must say, I haven't studied this in detail though. But I'm not so sure that human creativity will be overtaken anytime soon by AI in this regard. There's something to the way that we sometimes make connections that happen just by chance, by accident, that algorithmic systems do not do and cannot do at this time. So I'm personally not that worried by that. Yeah, that would be my take on it.
Clearly, the creative potential for programmers to come up with new and really insightful and creative ways of interpreting and problem solving and these kinds of things, which we then feed into programs. I guess where we're not there now clearly, but do you see a potential for a program to some extent motivate itself? In other words, up until this point, we have people who are trying to solve problems and then they put in a certain parameters so that the problem can be solved. And that's, I think, where some of the debate, at least that I've been reading about, exists, is whether or not you'll ever really be able to get a computer to take on that, or will computers always be, and by computers, of course, you highlight in your book that we are computers in the sense that we compute.
Mm-hmm.
And so in this case, I'm talking about digital computers, general computing machines. Do you see that jump being made in the future, possibly, or with the developments we have, or will it always be a sort of translation program, an abstraction program?
When you talk to AI researchers, they are way more skeptical about the dangers of AI that some prominent figures, Elon Musk and the late Stephen Hawking, have made, because the areas in which AI is very powerful right now are very, very narrow slices of human activity, human endeavors. And a general artificial intelligence, we are far away from this at this point. And there's also this idea that, intelligence is this open-ended, is something that exists on an open-ended spectrum, and that has no limits. But this is not really clear that this is the case. I mean, if you look at other natural phenomena like temperature, right? There's a lowest temperature that we have, or speed. Light speed is the fastest speed there is. So maybe there's a limit on intelligence as well. So this idea that intelligence is open-ended and there could be this explosion that we get intelligence that we can't even imagine, well, it is not clear that this even exists. So that's the first thing. The second thing is then people attribute to AI certain goals, and that AI systems all of a sudden develop their own goals, and that they completely ignore humans and the needs of humans and human goals, that are sometimes called the alignment problem.
Mm-hmm.
But it is not really clear to me how AI systems actually acquire these goals. I mean, we are ultimately motivated by evolution, right? Our needs are a result of us having been evolved over millions of years and having lived in the physical environment that we are living in. AI systems do not have that. And so it's not really clear that they would develop goals that are in conflict with those of humans, and that the alignment problem is really such a hard problem as it was always made to be. And then also that we all of a sudden lose control over AI systems, and that we wouldn't test AI systems to the point that we can be sure that they behave in a rational way. So I think these fears are overblown. And actually, talking to AI researchers, I think they do not see this danger. So this is kind of AI and computing taking over. And you're right, humans are computers in a certain sense, but it's not everything we do is computing. There are certain aspects of our lives that are algorithmic, that follow a certain plan. But then there are also other areas that aren't. I mean, if you listen to music, this is not really an algorithmic process, right? This is something else. And also, we should also remember that algorithms and computing has limitations. I'll talk about this also in the book. There are certain things, certain problems that cannot be solved by an algorithm. Actually, there is a huge number of problems that cannot be solved algorithmically. Mm-hmm. And then there's also the problem that even though certain problems have algorithms as solutions, they are just too inefficient. These algorithms that we know about today are too inefficient to solve these problems. So to believe that algorithms computing is taking over the world and enslaving humanity, I don't share those fears.
I guess that brings me to my next question, which is about what problems you think algorithms or computing are best suited to solve today. Because, of course, we've seen where they've come in tremendous speeds over the last few decades, particularly in certain branches like science, engineering, medicine. What kinds of problems are you hoping that computers will be able to better tackle over the next, say, few years, few decades? What do you hope to see develop in terms of the way people solve problems and what problems we tackle?
Yeah, well, now you're asking me to be a prophet, and
Well, what would you hope? I would say not what do you predict, but what avenues do you see a lot of potential?
well, as somebody who has written a lot of programs and made a lot of mistakes in doing that, I would start very humbly and say, well, it would be great if we could write software today that actually works and doesn't crash as often as it does. So, and also as a researcher in computer science, I really care a lot about developing software that is reliable and that does not do more harm than good. There's many stories in which software was employed that had really hazardous effects on human lives and on property. And that would be my first hope, that we get to the point where we can develop software that is more reliable, that we can trust more before we apply it into on more and more and more and more areas. But then, of course, many things that are easy to make mistakes with, if you can program this and you know that the program is reliable, well, then you can avoid mistakes. Think of anything. I mean, self-driving cars is maybe a good example. This will come sooner or later, but as we have seen, this is not a completely solved problem yet, because the question of safety, of course, is one that has to be solved. But then on the other hand, though, the prospect of avoiding stupid driver errors like checking your cell phone and then crashing into somebody else or killing a pedestrian, well, thousands of lives can be saved by employing this technology. Then, of course, I mean, since we're talking about self-driving cars, you get these philosophical problems that all of a sudden become relevant again, the so-called trolley problems that you certainly know about.
Mm-hmm.
And so what does a car do if it's faced with the problem of either, well, killing one person on the street or three children on the sidewalk? Or so how do we make these ethical decisions? And then in particular, if the decision is between, or the choice is between killing three pedestrians or killing the driver. I think people have studied this and have asked people about this. And most people say, oh yeah, the car should actually kill the driver in that instance and not the three pedestrians. But then when people were asked, well, would you buy such a car? Well, everybody said, no, of course not. So this is of course a difficult problem. It's a philosophical problem. Actually, this is a problem I think that cannot really very well be solved using a computer itself, right? This is something that humans have to discuss and ultimately decide on. Do you want to have culturally dependent ethics in every car? The car, depending on where you drive it, has different ethical rules of how to behave in these situations. But then there are people who say, well, these are all great topics for discussion, for seminars, but in reality, this will be really, really rare. And maybe it's best to really flip a coin, because this will occur so infrequently that it doesn't really matter in the grand scheme of things, in light of how many other thousands of lives can be saved by self-driving cars.
Mm-hmm. Well, that raises a really interesting point to me, which is, what do you think the relationship should be among, let's say, just for instance, computer programmers and philosophers? So they tend to be really different, like almost silos generally in universities in terms of what they're reading, in terms of who they're talking to, who they're talking about. But as you said, there are algorithmic problems like getting from point A to point B safely and securely. But then there are philosophical problems like whose life is worth more if you had to choose in a situation like that. What do you think the relationship should be between philosophers and people doing that kind of ethical process and the engineers and people doing the practical processes of making these self-driving cars, for instance? How should they relate in either at schools or in the workplace or what have you?
Well, there's different attitudes you can have towards this. I mean, there's always this idea of the responsible and ethical scientist who really judge all the implications that whatever technology they're working on has on society. But that's, of course, very hard to do. And in the same way, then, if you are an engineer and you're building an MRI machine and you know all about magnetics and electronics, but you don't know much about medicine, well, you probably have to talk to physicians who tell you what is important to visualize and trust their judgment on the specifics of the domain that you are about to implement. And I think the same is probably true in many areas. Now, when we're talking about ethics and morality, well, everybody is kind of involved. And we don't want to hand it over to the philosophers to tell us what the right thing to do is. So I think actually in this particular case, this is a conversation that all of society has to engage in, right? So we don't want to turn this over to a few philosopher professors in the universities.
Mm-hmm.
Yeah, there has to be a consensus, and then, well, whatever the consensus is, that has to be implemented reliably. So I don't think this is the responsibility of the computer scientist in this case. I think this is a responsibility that society has to take. And that actually brings me back to the point I made at the beginning. That is why people should know basics of computing, of what an algorithm is, what computers can and cannot do, so that they can, in an informed way, talk about this and form opinions and then make decisions.
Yeah.
And then there's one more thing I want to say. You said, well, philosophers and computer scientists don't have much to do with one another. Well, there is one area that is actually an area of overlap, which is philosophy of language. The work of Gottlieb Frege, for example, is very relevant to computer science, as some of the later philosophers, Bertrand Russell. Bertrand Russell, for example, with Russell's paradox, he was the inventor of types. It's a very important concept in computing. So there is some overlap between philosophy and computer science. But that's just a side note.
Yeah, no, and that's a great point, is that there is, I think, much more in common, especially with people who are taking a broad view of these two disciplines. And there's a lot of overlap, but I don't think there's a lot of overlap in terms of the businesses that are making the products and the universities that are writing philosophical books and stuff like that. Is there a way that you think it should be or it could be improved? Not even just these two groups, but in general, the people talking about ethical considerations and philosophical considerations and issues of what it means to be human and what it means to make decisions well and live a good life compared to computer programming courses, departments, that kind of thing. Is there an opportunity, you think, for more integration, or how would you see it working better?
So I don't really have a solution to this problem or to this tension. I mean, in many universities, students, undergraduate students at our university at least, they take a class in ethics. And there's always this notion of the responsible engineer. And so this is being tried to make engineers aware of the responsibility they have for society. But you can't turn engineers into philosophers. And you probably can't turn philosophers into engineers. So I think the best way to forward is to raise knowledge on both sides, to make people who care about ethics, morality, make them aware and know the basics of technology so that they can talk about it in an informed way and not be distracted by horror stories on the one hand or utopian visions on the other hand, but have a realistic view of technology and what it can do. And on the other hand, yes, have the engineers be informed about what the issues are in terms of ethics and morality, and then have them talk with one another. I mean, that's basically the only thing I can see we can do. And then actually on a broad societal level, I think the same thing has to happen as well, that people are aware of both sides, some basic understanding of science and scientific concepts and what is possible and what is not. And then also, well, what do we want as a society? What do we think are our goals? What do we value? And what do we want to achieve? And then try to bring these two together. And ultimately, I think if you don't have people on board, then, well, this won't work at all.
Mm-hmm. And so, if you had a platform to speak to people who may not understand computing as well as you would want,
Mhm.
and I'm thinking a lot of people who don't know very much at all about the technologies themselves are informed, or at least have images in their minds from some of the science fiction that you reference in your book, and from other, sort of horror scenarios that in a future reality people will all, have a Terminator situation or
Mhm.
something like that. What would you hope that they would get or that they would learn out of the misconceptions that you've heard? I'm sure you've heard a lot of misconceptions
Yeah.
about the technologies over time. What are some that you would love to correct or at least inform people about who aren't very familiar with the actual technologies?
I think in every science, a hallmark of every scientific discipline is to understand its limitation. I mean, in physics, you have fundamental limitations that characterize the field and the knowledge about the field. And we have this in computing as well. There are limitations of computing, and just understanding that. There's this so-called halting problem. If you have an algorithm and you want to decide, you want to look at it and decide whether or not it terminates, whether it will not run into an endless loop. That is an interesting problem. I mean, you would really love to know this, but it turns out you cannot write a program that looks at an arbitrary other program and decide whether or not it terminates. That's a very simple, seemingly simple problem, but this cannot be solved through a computer. This goes back to Alan Turing, the unsolvability of this halting problem. And to many people, this is surprising that seemingly simple problems like this cannot be solved by an algorithm. Now, if you know this, then you get, and you know some other limitations, you get a more realistic picture of what computers and algorithms can do and what they cannot do. And that, I think, gives you a more sober and realistic view of reality. And that lets you view horror stories and movies more as entertainment and not be freaked out by it, I think.
I'm just thinking at the same time, there's work being done or that has been done, like Thomas Kuhn, for example,
Hmm.
on paradigm shifting
Hmm.
and there's sort of incredible ways in which people have thought one thing and then it turns out that we're wrong. I mean, a lot of human societies and cultures have been wrong about things that they were very sure about.
Hmm.
To sort of play devil's advocate, how can we be confident that there are certain limitations when we keep seeing, or it seems that we're seeing limitations broken? What can help us be sure of, or at least
Hmm.
be conscious of these more sober takes on technologies when it seems that rules are being broken, even in physics, for example?
Right. So, while the revolutions in science and in paradigm shifts, while they do appear, well, it's also true that a lot of what science has produced in the past is still valid today. I mean, you could say that Einstein's relativity theory, well, invalidated Newton's theory, but
Hmm.
well, Newton's theory is still valid for most of what we're dealing with, right? So, and so you have this with many of these revolutions. So quantum mechanics, yes, at the fundamental level, reality is probabilistic or behaves in this probabilistic way. But then at our macro level, we are dealing with, we don't really have to worry about this. So that's the first thing I'd say. And then there are empirical facts, and then there are mathematical facts. And so the limitations I talked about, in particular the unsolvability of the halting problem, or Gödel's incompleteness theorem, for example, these are mathematical facts. And I don't think we will see a revolution that upends and creates a completely different form of mathematics that has a different form of logic that would be required in order to invalidate those facts. So I think those limitations we can be very sure of. There is the one open, there's an important open question in computer science that actually can have a huge impact. And that is the question of, it's the so-called P equals NP problem. So there are certain problems for which algorithms are known right now that have exponential runtime. Exponential runtime is really, really bad. And basically it means that you can't solve these problems in a precise way because the programs would just take too much time.
Hmm.
Now, some of these results depend on an assumption that a certain class of problems cannot be solved with algorithms that have non-exponential time. Now, this assumption could be wrong. This is an open problem for many years, and most of computer scientists believe today that P is not equals NP, which means these exponential algorithms, well, this is the best we can we can do. But should that turn out to be false, and should we actually show that this assumption is incorrect, well, then all of a sudden we can solve these very difficult problems efficiently. And that has, for example, immediate implications for the safety of transactions on the internet. Whenever you have a safe connection to your bank account, when this lock in your browser snaps, then, well, it's the encryption that is being used depends on the fact that it's very hard to take a huge number and compute its prime factors, to do prime factorization. And if all of a sudden we can do prime factorization very fast, well, that means all these secure connections would not be possible anymore. That would be a huge problem for the whole economy. And so, yeah, this can happen, of course. But there are certain, and the other solution to this problem, or the other disruption that could occur, is if quantum computers were to materialize. With quantum computing, you could also solve these problems that have exponential algorithms as solutions in sub-exponential time. That also could produce such a disruption and, well, if you wish, a revolution. But there are these fundamental problems of algorithms and computability that will not be affected by it.
If you were in conversation with people, especially those who are really worried about algorithms taking over the world and these potential disruptions, like major disruptions, what would your message be to the people who have been writing books or have at least been talking about stuff in the sense that we are going to hit a singularity very soon or something like that? Would you have a message for them?
Well, first message maybe would be to relax. So, yeah, the singularity, can you store consciousness in a computer, or can you have consciousness in machines? Well, that is a very difficult question. Maybe you can. So consciousness is not necessarily tied to the brain structure and to have this particular organic material that we have as brains. But then I do think there is something to our notion of consciousness and human existence that is dependent on us being embodied people, and we're living in an environment where other objects and interaction with other objects and people matters, that is not so easy to replicate in a computer. Of course, you can talk about creating virtual realities that try to do this, but there's a certain limit to how far you can get with this. So singularity, I'm skeptical about whether this can be achieved, at least in this short time frame. And I also think as far as computing disasters and computers taking over the world, I'm sometimes reminded of the Y2K problem. I mean, there were all these horror stories that came about, and everything will collapse when the year 2000 comes around. I don't know whether, I mean, most listeners will probably know this, that in the 1990s, 1980s, computers used two digits to represent a year information. And then when the year 2000 came along, 99 would turn to 00. And, well, who knows what happens, right? Sorting of data would not work anymore, and all kinds of horror scenarios were created. But then the year 2000 came and nothing bad really happened. So I think we are pretty good at adjusting to a changing landscape. And sure, there will always be more problems that arise with technology, with computing in particular. But then, well, we will find solutions to those. I'm very much reminded now of Steven Pinker's new book, Enlightenment Now, that I think is spot on this. I would agree with him with his view on this. Or David Deutsch's book, At the Beginning of Infinity, where he talks about the importance of explanations and how we can, in principle, how we are able to solve problems. That if you realize that, then future is not that frightening anymore, I think.
Yeah, well, and I think those are optimistic in a good way, in the sense that when people are really worried about these dangerous scenarios, there is evidence, as you said, with Pinker's book and others, of long-term looking at patterns and finding, that humans are quite capable of solving a lot of the problems that we can identify. What do you hope to do in the future? Are you planning on anything in relation to especially popular science again? Was that a good experience for you writing that kind of book? Because I know that you work on technical things, stuff that myself and listeners probably wouldn't have a clue of. Are you thinking of writing more that would be accessible, like this book, Once Upon an Algorithm?
Yeah, so yes, one thing I want to do is look more into this question of how much of what we're doing is actually algorithmic and what is not algorithmic. I'm interested in maybe creating a diary or having people create diaries of what they do every day and then classify what they do as either being just execution of an algorithm or, well, being not an algorithm. But even then, if you look at algorithms, there are some parts of algorithms that are not algorithmic. And maybe there are parts of activities that we do not classify as algorithmic that are algorithmic. Anyways, by doing that, we can get a better understanding of what the impacts of algorithm and computing is on our lives. And it would be interesting to see, to have data on this. The other thing, we're actually using this book also in teaching. And we have taught one section of an introductory computer science class and computer science orientation class using this what we call story programming approach. And we want to see how we can expand accessibility to computing through this approach. Computer science and computer scientists in particular, they suffer from some, not necessarily positive stereotypes. And this, keeps away people from the area that we could benefit from having in the area. So we could certainly benefit from having a more diverse set of students and then set of computer scientists. But many people are turned off by the geeky nature and by the requirement to code. There's this emphasis on coding, and even the word code and coding, I don't like this very much because it seems to indicate kind of hiding something. There's a secret, and in order to understand code, you have to decode it. That keeps us, I know, I've talked to a lot of students, keeps them away. They're afraid of this. And talking about computing and computer science concepts using stories opens this up to a wider audience. So we'll certainly explore this much more. My research is also focused on explainable computing, making programs and programming languages more explainable, which helps to make it more reliable. And that in that sense, these two areas fit together. Yeah, and in terms of what new book I'm going to write, I have not any concrete plans yet, but I could very well envision pursuing this kind of idea a little bit further, and maybe writing a book on how far algorithms go in affecting our everyday lives.
Yeah, well, I mean, that sounds like a really great work in combining storytelling and computing because, as you said, they seem to be so different, but that's as much a perception. I don't think it's so much a reality that they're both based on languages. And when you talk about language as opposed to coding, of course, it seems a lot more accessible suddenly. Yeah, I mean, that sounds really great. I want to follow up though on that idea of daily sort of algorithms or non-algorithms. How would you look, or what would be a very basic definition of an algorithm? If you were to take a diary and say this is not an algorithm, what would be some of the criteria for that?
Yeah, so basically an algorithm is something that you could write down, right? So you could basically, if you look at an activity and if you could write it down and give it to somebody else, and that somebody else could replicate it to a certain degree of precision, then you would say, yeah, this is algorithmic.
How would you know that it couldn't be written? Because technically, yeah. I mean, couldn't you, if you're writing a diary of what you've done, couldn't someone replicate your day?
Well, but suppose part of your day is listening to music. So, now you have this experience. You sit down for 15 minutes and you listen to a music piece. Well, you could do the same thing, but the 15 minutes in which you sit there and have this music experience, but that by itself is not, the experience that you have is not really an algorithm that runs. Well, maybe there's some algorithms in your brain that run, but we don't really understand what exactly is going on there. I mean, maybe neuroscientists can tell you what processes in the brain are active and so on and so forth, but you could not replicate the same experience in another person. At least I think that is not possible at this point. And or let's say you're playing an instrument, okay? You're playing piano or the guitar. You could say, well, I played this instrument. And then the scores for this for this piece, well, that certainly can be viewed as an algorithm. But if somebody else is playing this piece, it's most certainly will not sound the same way that you played it. And well, maybe their skill level is different. Maybe they can't actually play that. They make mistakes. So the whole experience would be different. So it's not so clear cut that activities that look on the surface as being algorithmic are algorithmic all the way down, and whether they are not parts of the activities that are non-algorithmic. And so I don't think there's a clear-cut separation. That's why I said that there's clear-cut algorithms. I mean, getting dressed in the morning. Yeah, I mean, even though there are minor differences in which you put on a shirt or your socks or whatever, basically, if you tell somebody, well, this is the way you're getting dressed, they probably could do it. But then if you have to tie a tie, well, there you can see on TV that there are some good results and there are some not so good results. Some of this is certainly algorithmic, but then some parts of this may not be so clear cut. Could be maybe in principle described as an algorithm, but well, maybe we don't do it, and it would require too much detail in order to be of interest.
Well, it's really interesting, that whole project, because it seems to point to something that I think most people are interested in who talk about this in any way, philosophers, cultural studies, computer programmers, is that seemingly intangible element that computing almost gets to but never quite seems to get to. And I think that's why some people are really excited about computing, maybe getting further into that realm, while others are cautious about that. But it's a sort of phenomenological aspect that keeps it in a sort of tension, I think, with some other versions of philosophy and epistemology. But no, it sounds like a really cool project. Yeah, I really appreciate you taking the time to speak to me today, Martin. Is there anything else that you wanted to talk about, or that you were thinking you'd like to mention?
Not really. Well, maybe one more thing that I could mention is that I was often asked why use stories to explain computing and not anything else. And I think the stories work so well because, well, first of all, we can find computing in stories, but also we empathize with stories, right? We can really see ourselves doing the same things that the characters in the stories are doing. And that opens up immediately to the metaphors, and we immediately can grasp the impact of the computing concepts that are being employed. And that, I think, is a good argument for using stories to do that. And it could be, I've been contacted by some people who want to use that approach in other areas of engineering and science as well. And I think it's a good idea. And well, otherwise, I want to thank you for this very nice interview. It was a very great experience to talk to you.
Yeah, well, like I said, I appreciate it very much. And yeah, Once Upon an Algorithm is an excellent example of how stories can be used to teach seemingly very sort of logical and dry concepts in a way that does create empathy and excitement, I think, for readers. So thank you for writing it, and thank you for speaking to me today.
Well, thanks for having me.